All right, let's go ahead and start our next units on thermodynamics. We'll start off with first law of thermodynamics. We'll actually get to that in just a bit. Definition of energy. Technically, energy is the capacity to do work. We'll see later on that work is defined as force times distance. So if you apply a force and something moves, then that means that work is being done. So we'll talk later about work. There are two main types of energy. They are kinetic energy and potential energy. Kinetic energy is energy of motion, so things that are moving possess kinetic energy. Make sure you also understand that kinetic energy is related to temperature as well. So formula for calculating kinetic energy is 1/2 mv squared. This is a small v, so be careful. There's a difference between a little v and a big V. So m is the mass of the object that is moving. Technically, that's in kilograms. And then little v here, again, energy of motion, is the velocity of the particle in, that says meters per second. So we've talked about this before. Take kilogram times meter squared per second squared. Kilogram times meter squared over second squared, and that is the same thing as a joule, which is the SI unit of energy. Potential energy is the energy that a system possesses by virtue of its position or composition. For example, suppose you have two attracting bodies, say Na plus ion and Cl minus ion, and if those particles are at a certain distance from each other, so if they're not touching, but if they're separated by a certain distance, then they possess a certain amount of potential energy. So attracting bodies that are not touching possess potential energy. By composition, mainly we mean that energy is stored in chemical bonds, and so that's what's meant by virtue of its composition. All right, first law of thermodynamics states that the combined amount of matter and energy in the universe is constant. So you can't make matter. Matter cannot be destroyed. You cannot make energy. Energy cannot be destroyed. But matter can undergo changes. It can change its form. Likewise, energy can change its form. You can change, say, from kinetic to potential, or potential to kinetic. And then there's also energy can be transferred, as we'll see in a second, from one object to another. Speaking of which, some thermodynamic terminology. The system refers to the part of the universe you wish to study. Or another way I like to describe the system is the substance that is undergoing the change. So let's say you have a substance that is undergoing either a physical or chemical change. That substance is the system. So it's the substance that the change is occurring to. And then everything outside of the system you are studying is known as the surroundings. Properties of a system, we have these things called state functions. Not that important, but some examples of state functions are pressure, volume, and temperature. These refer to the conditions of a substance. State functions technically are things that are independent of the pathway taken to arrive at something. Again, not that important for this class. What is important, though, is energy flow. We'll start off with the symbol for energy content or heat content. The symbol is H, or heat content, energy content. This is known as enthalpy, so fancy word kind of for energy. We've seen before delta H, and so that's delta H is change in enthalpy or change in heat content or change in energy that accompanies some chemical process. Sometimes enthalpy or heat content is symbolized by Q, like we see in Q equals MCAT. That Q is referring to heat content, technically transfer of energy that occurs. All right, energy flow, exothermic processes. During an exothermic process, energy flows out of the system being studied, out of the system, and absorbed by the surroundings. So energy is given off, and that energy is absorbed by the surroundings. In the case of an exothermic process, actually, let's ask this. True or false? All chemical processes require energy. That is true, of course. True or false? All chemical processes release energy. That also is true. So whether a process is endothermic or exothermic depends on the amount of energy required compared to the amount of energy released, as I'll show you in a little bit on a heat content diagram. So something else to keep in mind for an exothermic process, what is always true is that the energy of the reactants is greater than the energy of the products. That's kind of a weird symbol there. So let's try that again. All right, a little better. So the reactants have more energy than the products. Remember, when you calculate delta H, technically we do it this way. So it's the energy of the products minus the energy of the reactants. And if the reactants have more energy than the products, then delta H will be negative. Take a look on page 549. We have there a heat content diagram that's called for an exothermic reaction. So let me draw that in the space here that I have on my slide. You can see in the book on the y-axis can be a number of things: energy, enthalpy, H for enthalpy, or potential energy. I like to put potential energy like the book has. And then on the x-axis is reaction coordinates or reaction progress. So over the course of that chemical process. And so let's go ahead and draw something that's similar to what's shown there. So this number here, whatever that number happens to be, that's the energy of the reactants. And if we go over here, this number here, whatever that is the energy of the products. So notice that the products have less energy than the reactants. If what you make has less energy than what you started with, then that process overall is going to be exothermic. Well, what happened to the difference in energy? So if what you make has less energy than what you started with, where did that excess energy go? That's the energy that was released to the surroundings. In fact, so on our heat content diagram, that is our delta H. So delta H is the difference in energies of the reactants and products. From here to here, that is the total amount of energy that is required for the reaction to occur. I think there's a name for that, isn't there? The energy that is required for a reaction to occur. This is known as activation energy. And from here to here is the total amount of energy released by the reaction. So what do you notice about the energy required compared to the energy released? Well, it looks like more energy is released total than is required. Therefore, this process is exothermic. And notice that the difference between the energy, this should be all the way down here. The energy required and the energy released is delta H. That's your difference. All right, how about endothermic? During an endothermic process, energy is absorbed by the system from the surroundings. So energy flows into the system. Where does that energy come from? Just doesn't come from nowhere. It comes from the surroundings. By the way, when an exothermic process occurs, what happens to the temperature of the surroundings? Well, since energy is being released to the surroundings are absorbing energy, the temperature of the surroundings increases. Conversely, what happens to the temperature of the surroundings during an endothermic process? Well, since energy is being transferred from the surroundings to the system, the surroundings are losing energy. The surroundings temperature will decrease. So in this case, endothermic process, the heat content or energy of the products is greater than the reactants. So again, going back to our equation for calculating delta H, It's got to be in this order. If the products have more energy than the reactants, then delta H is going to be positive. There's an example of an endothermic process. Not sure if I showed this to you last year or not. A reaction between barium hydroxide and ammonium nitrate. I use ammonium thiocyanate and barium hydroxide, similar reaction that occurs. And so this reaction is extremely endothermic. So endothermic that if you put a little bit of water on that wood there and put the flask on top of the wood, the water will freeze. The lowest I've gotten is negative, I think 29 or negative 30 degrees Celsius. So I've seen a change in temperature of about 50 degrees Celsius during that reaction. We're talking about probably the same quantities as shown in the book, maybe a little bit more of the chemicals. So endothermic. Let's do this. It's not in the notes, but maybe we can add this in the margin. Heat content diagram for an endothermic reaction. Let's draw that. So same axes, we have potential energy on the y-axis, a reaction progress on the x-axis. Get something like this. Whatever this number is, that's the energy of the reactants. Whatever that number is the energy of the products. Difference in energy of the reactants and products is our delta H. From here to here, that is the total energy required for the reaction to occur. That's our activation energy. And from here to here, that is the total energy released during the reaction. What do you notice about the amount of energy required compared to the amount of energy released? We see that more energy is required than is released. If this is the case, that means that process is endothermic. Something else you'll notice that during this process, according to the graph, what you make, the products, have more energy than what you started with. If what you make has more energy than what you started with, then again, that process is endothermic. Well, where did the energy come from to make those products? Well, the energy came from the surroundings. So remember, energy is absorbed from the surroundings, allowing for the transformation of the reactants into the products. I kind of mentioned this already before with the first law of thermodynamics, law of conservation of energy. Energy is neither created nor destroyed during chemical or physical changes. Not true for nuclear reactions, but true of chemical and physical changes. So energy can be transformed from one type to another. Energy can be transferred from one substance to another. Speaking of a transfer of energy from one substance to another, we have calorimetry. I'm going to read the first part that's not in parentheses because it can go either way. First, energy is transferred to a process undergoing a chemical or physical change. That would be endothermic. From water. So there's always water involved in calorimetry. Or, I'm going to read the part in parentheses, energy is transferred from a process undergoing a chemical or physical change. That would be exothermic to water in a well-insulated container that minimizes the amount of heat lost or gained from the surroundings. So this well-insulated container that minimizes energy transfer with the surroundings is known as a calorimeter. There's a couple types of calorimeters. One is known as a coffee cup calorimeter. There's a picture in your book on page 552, so take a look there. Coffee cup calorimeter is also known as a constant pressure calorimeter. Because it's open to the atmosphere, even though it has a little lid on it, that lid is loose in the picture. Because it is open to the atmosphere, then the pressure is constant. There's another type of calorimeter known as a bomb calorimeter, and a bomb calorimeter is known as a constant volume calorimeter. So it's a rigid container that's sealed, and therefore the volume remains constant, and the pressure changes in this case. So we're going to focus on coffee cup calorimeters. Let's do this. Um, are calorimeters perfect insulators? Imagine you have a cup of hot chocolate. Can you feel the heat, the temperature of that hot chocolate outside of the cup that you're holding? Certainly. Why is that so? Well, that's because the calorimeter itself is not a perfect insulator, and it does absorb some of the heat from the hot chocolate. So let's do this. Let's, in this space, let's write an equation. So let's go with this. That says released. So the energy absorbed or released by a reaction is equal to, so absorbed if it's an endothermic, released if it's an exothermic reaction. Sorry, I have kind of a lot of stuff to write in here. So remember, you have water in the calorimeter. So the energy absorbed or released by the reaction is equal to the energy absorbed or released by the water. Again, depending if the process occurring in the water is endothermic or exothermic. And since calorimeters are not perfect insulators, I should not do that because that looks like a greater or a plus or minus, not a plus. Energy absorbed or released by the calorimeter or the water plus energy absorbed or released by the calorimeter itself. Gosh, you're just going to have to take my word for it that that says calorimeter. So let me read this again, make sure I understand this. I'll do it one way. So let's say you have an exothermic reaction. During an exothermic reaction, the energy released by the reaction is equal to the energy absorbed by both the water and the calorimeter. Both objects are absorbing the energy. It's an endothermic reaction that occurs. The energy absorbed by the reaction is equal to the energy released by both the water and the calorimeter. So this is very important. We can't always assume that the calorimeter is a perfect insulator. And so if it's not a perfect insulator, then we need to account for the energy transfer that occurs with the calorimeter itself. Now, usually, and in fact, up to this point, even in Chem 1, we assumed that the calorimeter was a perfect insulator. So it says the amount of energy gained or lost by the calorimeter is usually so small that it is ignored. And so in that case, when we're doing any calorimetry problems, we just consider this and this. But again, if your calorimeter is not a perfect insulator, if there's information that indicates that the calorimeter is not a perfect insulator, then we must also include energy transfer with the calorimeter itself. And so what is that information that would imply that the calorimeter is not a perfect insulator? You may be given something called the heat capacity of the calorimeter. So heat capacity is the amount of energy that needs to be added or removed to change the temperature of a substance by 1 degree Celsius. So the units are joules per degree Celsius. How much energy in joules is needed to increase temperature if it's an endothermic process relative to that substance. 1 degree Celsius, or the energy that must be removed to cool a substance 1 degree Celsius. Now, don't confuse heat capacity with specific heat capacity. So specific because we're talking about a specific amount. Heat capacity is independent of amount. Specific heat capacity, or just specific heat, is dependent on the amount. So it is the amount of energy that needs to be added or removed to change the temperature of 1 gram of a substance 1 degree Celsius. So units for specific heat are, I'm going to give you a couple actually, joules per gram degree Celsius or joules per gram Kelvin. So remember, the difference between Celsius temperatures and the corresponding Kelvin temperatures are the same. So either joules per gram degree Celsius or joules per gram Kelvin. Hopefully you have the specific heat of liquid water memorized. Remember, there are different values for ice, liquid water, and steam. So liquid water is usually what we're dealing with, especially in calorimetry. And we'll just go 3 sig figs. If you want to go 4 sig figs, that would be 4.184. 3 sig figs, 4.18 joules per gram degree Celsius is fine. All right, let's take a look at some examples involving calorimetry in 552.15.1. It says we add 3.358 kilojoules of heat to a calorimeter that contains 50.00 grams of water. The temperature of the water in the calorimeter, originally at 22.34 degrees Celsius, increases to 36.74 degrees Celsius. Calculate the heat capacity of the calorimeter in joules per degree Celsius. The specific heat of water is 4.18 joules per gram degree Celsius. Now, here's what's going on here. You take some energy, add it to the water in the calorimeter, and not only is the water going to absorb energy, but the calorimeter is as well. Something to keep in mind is that the change in temperature that occurs to the water inside the calorimeter is also the same as the change in temperature of the calorimeter itself. So, first thing we want to do is calculate the amounts of energy absorbed by the water. So you have 50 grams of water, specific heat 4.184, and the temperature increases by 14.40 degrees Celsius. So the water itself absorbs 3.012 times 10 to the third, or 3.012 kilojoules of energy. Now notice that is less than the total amount of energy that was added. Originally, it said in the problem that you added 3.358 kilojoules of energy. Well, where did the rest of that energy go if it didn't go into the water? That's how much energy the calorimeter absorbed. Usually heat capacity, again, is given in joules per degree Celsius. So take the difference in those energies in joules, which is 346, divide by the change in temperature, and you get to the heat capacity of the calorimeter, in this case 24.0 joules per degree Celsius. All right, let's go to 597. Jump ahead quite a bit. Example, or exercise rather, 61. So calorimetry is later on in the textbook. Number 61, and let's just do, I don't know, let's just do letter A. Same situation, you're trying to determine the heat capacity of a calorimeter, also known as a calorimeter constant. Go ahead and do that now. Pause the video now, please. So here's our setup. You take some warm water, you mix it with cold water. The warm water is going to release energy. The cold water is going to absorb energy. At some points, thermal equilibrium will be reached where the temperature of the warm water and cold water or cool water are the same. So warm water cools down, so it calculates using the calculate the energy released by using Kugel's MCATs. Here I don't really care about the delta T, just make sure it's positive in both cases. So just take bigger minus smaller temperature. So 3 sig figs, 7,870 joules of energy released by the warm water. Calculate next the energy absorbed by the cold water. Again, temperature this time increases from 22.8 to 39.7, so Q equals MCAT. 7,070, again 3 sig figs, joules of energy absorbed by the cool water. Well, notice more energy was released by the warm water than was absorbed by the cool water. Why? Well, the calorimeter absorbs some energy as well. And the difference between these is how much energy the calorimeter absorbed. So I need 3 sig figs in my answer. So it's 800, but I put that in scientific notation so we can have 3 sig figs. Next is we take the total amount of energy absorbed by the calorimeter and divide it by the change in temperature of the calorimeter. So again, we'll assume that the initial temperature of the calorimeter was the same as the initial temperature of the cool water. And the final temperature of the calorimeter is the same as the final temperature of that system, or in the case, both of the water samples, if you will. So we get 47.3 joules per degree Celsius. Look at another example, go to 553.15.2. Let's read along because this one's quite a bit different. This is more applicable to what we do with calorimetry in this class. A 50.0 milliliter sample of 0.400 molar copper 2 sulfate solution at 23.35 degrees Celsius is mixed with 50 milliliters of 0.600 molar sodium hydroxide solution, also at 23.35 degrees Celsius, in a coffee cup calorimeter of example 15.1. So we have a chemical reaction that's occurring. After the reaction occurs, the temperature of the resulting mixture is measured to be 25.23 degrees Celsius. What does that mean about the reaction? Take a look at the initial temperature of the solutions compared to the final temperature of your resulting solution. Temperature increases, which indicates that this reaction is exothermic. The density of the final solution is 1.02 grams per milliliter. Calculate the amount of heat evolved, the amount of heat released, energy released by the reaction. So assume that the specific heat of the solution is the same of that as pure water. All right, so we have our chemical equation. Now, something to keep in mind is determining the limiting reactant. So how much energy is released by this reaction depends on the amount of the limiting reactant. So that'll be for future calculations. And this one, it really doesn't matter since we're just calculating the energy released. If we were calculating, say, delta H, which has units of kilojoules per mole, that would be per mole of the limiting reactant. So don't worry about that at the moment. So we need to calculate the energy associated with this reaction. So we need to calculate using Q equals MCATs. First, though, take the density of the solution and multiply it by the volume of the solution to get the mass. So remember Q equals MCAT, so we need mass. So mass of the solution, 102 grams. We'll assume the specific heat, same as water, 4.18. Change in temperature from 23.35 to 25.23. That's the energy that is just absorbed by the solution from the reaction. The calorimeter, we'll assume, also is not a perfect insulator. And so we need to, in fact, in 15.1, we calculated the heat capacity of the calorimeter. So we'll use that, 24.0 joules per degree Celsius times the change in temperature of the calorimeter. Add that to the energy absorbed by the solution, and that'll give us the total energy released by the reaction, in this case, which is 846 joules. If we wanted to calculate, again, the heat of reaction, we take 0.846 kilojoules divided by moles of the limiting reactants. That will be later. All right, 598. Let's take a look there. Number 65A. Let me see if I need to tell you anything about that. Oh, speaking of delta H, there it is. So if we have a limiting reactant situation, make sure to divide by moles of the limiting reactants. All right, let's go ahead and pause the video and work on that now. Alrighty, here's our setup. So we have 20 milliliters of one solution that we combine with 30 milliliters of another solution. So that gives us 50 milliliters total of solution, density 1.02 grams per milliliter. So that'll allow us to find the mass of the solution, times the specific heat, times the change in temperature, which is 2.947 degrees Celsius. And so the energy absorbed by the solution from the reaction is 629 joules. The calorimeter itself is also absorbing energy. So again, same change in temperature as the solution. The heat capacity of the calorimeter is 27.8. Sorry, I ran out of room here. 27.8 joules per degree Celsius. So the calorimeter itself absorbs 81.9 joules. Take those, add them up. Because of our significant figures, we end up with 711 joules of energy total released by the reaction, absorbed by the solution that those chemicals are in. Letter B is to calculate delta H for the reaction, the change in heat content. I mentioned before, delta H has units of kilojoules per mole. Total amount of energy in kilojoules released per mole of substance undergoing the change. And in this case, per mole of the limiting reactant. Remember, when the limiting reactant runs out, reaction stops, no more energy is being released, and so we always want to use that substance. So in this case, it looked like the limiting reactant was the sodium hydroxide. They react in a 1-to-1 ratio, and there's less moles of sodium hydroxide than the acetic acid. And so I put the total amount of energy, 711, convert that to kilojoules first, and divide it by molarity times liters, which is moles, and we get 56.9 kilojoules per mole, except you're going to see a big deduction if you leave your answer like this. This reaction, if you recall, is exothermic. Does anybody remember how to identify that the reaction is exothermic in the delta H value? We already talked about it before. Since the reaction is exothermic, that means delta H must be negative. It's not going to say that on your calculator. So you have to add that if the reaction is exothermic. College Board takes off 1 point out of 2. So 50% if you do not include the sign for delta H. So be careful. All right, that concludes this lesson. I'll give you some practice later. Thanks for watching.